In this video, we're going to talk about AI through my YouTube channel, AI Nexus. Please do subscribe to this channel. I'm Dr. T.V. Geeta. So, in this particular video, we're going to talk about how AI finds oddities, relationships, and hidden patterns. So, the first one is anomaly detection, which is spotting unusual behavior. Next is association learning, finding items that occur together. And density estimation, we are finding the hidden structure or the data concentration in the data set. Okay, so this is video is going to tell you how machine learning identifies outliers, understands relationship, and finds hidden structure in the data. Now, next is anomaly detection, the first one. So, this is to find the unusual and prevent damage. So, what is anomaly detection? Anomaly detection is an unsupervised machine learning technique used to find data points that are rare, unusual, or suspicious because they differ significantly from the normal data. Examples include credit card fraud detection. So most card detections are under $100. This is a simple example. When you find a transaction that is $5,000 and from another country with unusual time, then you likely to be fraud, so tag it. Then machine failure detection. Here machine vibration is normally steady. Then you find a peak. Then there is an anomaly. So it may indicate a fault or failure. So why does anomaly detection matter? It protects systems from rare but high impact events that cause high damage. And it detects system failures early so that you can do predictive maintenance by preventing system failures. Then protects digital systems from cyber attacks and helps detect rare diseases early, and it enables better data quality control. So a mathematical view, a very simple view is most data points cluster around a normal region. Now points that are far away with very low probability is probably an anomaly. Next we'll go to anomaly detection of how it works. So the first one is collect normal data. Here you collect lots of normal data and little bit of anomalous data. Then you do data processing, that is handle missing values, normalize features, remove noise, clean the data. Then you do feature engineering, which is very important because better features will give to better anomaly boundary. Then you learn the normal behavior. You can use any model for that. Then you measure deviation. For each new data point, you output a anomaly score. So the higher score means it means more abnormal. Then you have a threshold decision. If the deviation is greater than the threshold, you mark it as anomaly. From a geometry viewpoint, imagine every data point is a dot in space. So normal data forms a cluster. Anomaly is a point far away from that dense region or the cluster. Okay, so now the credit card transaction example, the normal transaction are given and the pattern is learned by the anomaly detection model. And then when you give it, and also you have given it the normal and the abnormal, then you give an anomalous transaction. It is away from the normal pattern, then alert is given. Next, we go to association discovery. This discovers hidden relationship. Other words, what occurs together. So, in retail, products bought together. In healthcare, could be symptoms and diseases that occur together. Web usage, page visit patterns. Manufacturing, conditions causing defects. And analogy would be if Rahul is there, Amit is likely to be there, sure. So there is a strong association between Rahul and Amit. This association discovery was initially designed by retail scenario. What items occur together in a basket? So it's called market basket analysis also. Now let's take the steps of association detection. So first you collect the transaction data, large set, but here we are just taking a toy example. And this each transaction, what all was bought together. Then from this, you find out frequent item sets. Here we are doing 1 item set, 2 item set and 3 item set. And then you keep only those item sets which is having a support count of greater than or equal to 40%. Support count is count of item set in the transaction data set. Then the third is generating rules. Here I have, for example, shown you only one example from 2 item set and one example from 3 item set. And so with that you are forming the rules, bread and diaper. So bread, if you buy, diaper you're likely to buy. If you buy diaper, you're likely to buy bread. And similarly for 3 item set. Not that bread and diaper together, if you buy juice, you're likely to buy, and so on. Now you have to evaluate the rules. For evaluating the rules, you have support. How common is a rule? Then you have confidence. If item X happens, how often does item Y also happen? This is called how reliable is the rule. Then you have lift. Is the rule stronger than something that occurs at random? Once you evaluate, then you keep only the strong rules which has a minimum support, minimum confidence and minimum lift. Then we have density estimation. So density estimation is an unsupervised machine learning technique that estimates how data is distributed in space. So where it is crowded and where it is sparse. An analogy is, imagine a beach and there are many people near the water and a few people in a far rocky corner. So is this person standing in a normal place? In the crowded area means normal, alone means unusual. So density is nothing but the number of people per area. So high density means normal, low density means anomaly. So examples include fraud detection, detecting rare events, medical diagnosis, detecting rare conditions, customer behavior, unusual customers, scientific analysis, for example, rare star detection, generative modeling. This is actually the foundation of the current AI, which is generative AI. So why density estimation matters? It detects normal versus abnormal. It is the foundation of generative AI, helps in decision making, works without labels, improves other ML models, and it allows a deep understanding of data. The mathematical perspective here is we are actually trying to estimate the probability density function. Here P of x is the density at point x, and we have to find the probability of the region, which is P of A. So this is given here, and we get the probability of the region A, or the probability density function. Now you have a true distribution, you have an estimated distribution. The closer they are together, the better. So how to measure success? You measure the distance between the true distribution and the estimated distribution. The lower the distance, the better is the estimation. Now let us compare unsupervised learning techniques in basically which can be defined as finding patterns without giving labels. So the simple question that each technique answers, let us look at that first. For clustering, it is which items are similar. So how do we organize unlabeled data? That is by grouping similar data, and the example, the output is shown there. And then we have the next one. Can we compress this data? That is dimensionality reduction. So we reduce the features into a structure and basically we simplify data. So from a higher dimensional data, we get a lower dimensional data as shown in the output. Then we have anomaly detection, which is what looks strange, which points are rare or abnormal. So you're actually finding unusual data, and that is shown as outliers in the output. Then we have what tends to happen together, which is association discovery. What items or events occur together. This is we are finding the co-occurrence patterns, and we get a rule. That is, if you have A, B will be there. Then we have the final one, which is density estimation. How common is this value? Where is the data concentrated? In fact, here we estimate probability distribution, and that is also shown as output.